The enlarged claw may develop on either the left or right side. The second claw remains comparatively small and retains its original versatility, allowing the animal to manipulate its environment with precision. Together, these appendages represent a clear division of function, with one adapted for fine-scale interaction and the other for the generation of force. It is at this point that these lineages of pistol shrimp diverge most clearly from more familiar crustacean forms. The enlarged claw does not operate by crushing or tearing in the conventional sense, but through a fundamentally different process, one that relies on the physical properties of water itself. The functional difference between a conventional claw and the snapping appendage of a pistol shrimp lies not only in its size, but in the way it stores and releases energy. In most crustaceans, the claws operate through simple muscle movement, closing in a controlled motion to grasp or crush prey. In pistol shrimp, this basic arrangement has been modified into a system that allows force to be accumulated gradually and then released almost instantaneously. The enlarged claw is composed of two uneven parts, a movable segment, often described as a plunger, and a fixed segment that forms a corresponding socket. When the claw is opened, the plunger is drawn back and held in place by a specialized locking mechanism within the joint. This position is not passive. Muscles within the limb continue to contract, loading the system with potential energy while the structure remains held firmly in place. This creates a form of biological spring loading, in which energy is stored over a longer period of time than it takes to release it. The advantage of this arrangement is that it allows the shrimp to bypass the normal limitations of muscle speed. Rather than relying on the rate of contraction alone, the system separates the phases of energy storage and discharge. Once triggered, the lock is released, and the plunger is driven forward into the socket with extreme speed. The motion itself occurs in a fraction of a millisecond, faster than the surrounding water can move to accommodate the sudden change in position. As the plunger closes, it forces a narrow jet of water outward from the claw at very high velocity. It is this rapid displacement of water that initiates the most significant part of the process. As the jet moves forward, it creates a region of low pressure immediately behind it. Under normal conditions, water resists separation, held together by the natural cohesion of water molecules. However, when the pressure drops sufficiently, the liquid can no longer remain intact, and a small cavity begins to form. This cavity, known as a cavitation bubble, expands rapidly as the difference in pressure remains. For a brief moment, it remains stable, carried forward by the momentum of the surrounding fluid.